beta D gamma, it's supposed to be
Yes.
significantly larger and things. So
Exactly. So here, I mean, I will go in the next step to more I mean, rare decays and
okay, okay.
indeed it is, and it's getting there where you start to go. I mean, you remember when I was talking about interference between new physics and standard model. Then you get with a smaller contribution from the standard model, but yeah, big effect can be seen maybe more visibly with this B2D gamma mode, but very suppressed. So we talk about B2 rho omega or B2 omega gamma, sorry, gamma, not omega. And consequently, the efficiency it's more difficult. The background is much higher. You have only pion in final state. So you need much more statistics. So indeed, I mean, we just observe those modes. In fact, we are in the same situation of, Cleo observes B2S gamma, and we kind of study its observables. And for B2D gamma, it's a bit the same thing. We observe Belle, observe B2D gamma, but probably Belle 2 will have the statistic to study, including those observables like CPS.
Okay. All right. So I think we should
Go ahead.
start now. So
Okay. So yeah, as we were just talking about, I mean, we started a B2S gamma, and what I like in B2S gamma is that we had enough statistics, even with the B factor, to get some precise measurement. And we started also to discuss the importance of forming some observables which are robust to theory predictions, and also which are experimentally robust, so we can take full advantage of the statistic we are having. And as we have seen, the branching ratio are very quickly limited. So in the sense that they are the more precise observable we obtain, but beyond that, we can do much more. So one example we have seen this morning are symmetries, CP asymmetries. So the behavior of, in the case I was showing, B plus versus B minus, or B0 versus B0 bar. So this was, let's say, the strength of a B factory, then to be able to be as efficient almost with mode with a neutral in the final state, then mode with charge tracks. Here, I mean, I had this example. We were talking. I put it back because we were talking this morning. Guy just, I mean, I was showing a few things about LHC, and Guy gave you also very nice first lecture on LHC, and I was talking about this let's say. Two paths of a same quest, as I said earlier. And another typical example before going to B2 SLL is in fact Bisabest to Mu. And I mean, just I use it here as an introduction of the fulfilling all the requirement of a powerful rare BDKs, or in this case rare Bisabest decays. So I had also these slides a little bit kind of summarizing, if we want, what I have said earlier when I was trying to rebuild the Belle and Belle 2 detectors, and when I put the environment in place for Belle 2, and also what you heard about LHCb, and in this slide you have the different information side by side, and now you can have a kind of a compilation of the advantage, disadvantage. So as we have seen, epsilon 4s plus minus collider allows some definitely clean events. And what would be the strength here is the efficiency. Efficiency of almost any possible final state, efficiency of the flavor tagging. Later, Guy and myself might mention some time-dependent analysis using, needed the flavor tagging, the flavor information from the bee, and this has a very high efficiency. This is the power of having only 2B in the events. Also the B tagging, which is heavily used. I'm just talking a few minutes for a B factory where you have to reconstruct the other B. And once you reconstruct it, you know that there is no other information because there is no fragmentation like you would have in, Z2 BB bar, or you will have an LHC B. So those are the strengths. And of course, on the other side, the cross section at the LHC B is completely impressive in terms of B produce. There is also the displaced vertex, and I put also other strains with well separated. It doesn't mean we don't have separated vertex and we cannot use this information. This is actually the core itself of this asymmetry B factories, and they have been able to observe and measure precisely CP violation, but the boost is much smaller. So here, just to give you an idea, we talk about typical decay length of a few hundred microns versus decay length of several millimeters, 7 millimeters. So, this is, even if you see this very busy event display of LHCb, in fact, this is probably not the way, this projection is not probably the way to see the events. I mean, if you see in terms of displaced vertex, this dimension offer you, in fact, a way to clean up the events with a very impressive efficiency. So the event display is just the projection you want to show, but it's not what necessarily the analysis procedure see, and that's what is important. The cumulative data also, we talk about the instantaneous luminosity, we talk about the cross section, but the integrated luminosity is also, and you see the luminosity at B factory is much larger. We talk about inverse autobahn. Whereas in LHC we talk for now at least in terms of inverse femtobahn. So you gain back some few order of magnitude. Okay, so yeah, just as an introduction on reintroduction of this ultra rare process, I was talking about B2S gamma. Then just now we mentioned this similar penguin, but instead of VTS, it's VTD, and so B2D gamma. So very suppressed. Total cross section, branching ratio of B2S gamma was in 10⁻�3, 10⁻⁴ for the exclusive decays. And here, for example, in the case of Belle II B, which was one of the main first goal of LHCb, the golden mode of LHCb. In fact, we talk about 10⁻⁹, so you can see. But again, this is a good example because here, what also is important is that people have predicted precisely the branching ratio expected in the standard model, while you have also some new physics model introduced to show some enhancement or suppression of this branching ratio measurement. And another thing which is interesting is like all this effort, we have a small window in our most of the time in our career, either we stay or not in the field, and we see through a small period. But it's interesting when you compile the result that in fact this mode, which is now observed by LHC is in fact the result of a very long quest, and you see it in other rare decay search, that it goes through 30-40 years and generation of the experiment, and before and we will see also the tau physics, where we were talking when introducing Guy about the effort of building the next generation of a tau factory, or producing more tau to reach sensitivity, or a better sensitivity to those lepton flavor violation decay. Okay, and then as I said, I mean, the ultimate goal is to observe it, and in most of the cases, unfortunately, it's observed at the level of a standard model. But all this generation before observing it made this effort and push down the limit of it. And just here, I just flashed one recent result. I think it has been updated since, of course. But anyway, where the observation of B-sub-S mu was done by a single experiment. So at first it was with a combine, and you will hear probably later about the CMS result on this, but just to show that as a single experiment, you reach 10⁻⁹. It's probably in the B sector is probably one of the most one of the lowest branching ratio measure for any decay, but with a strong observation, very clear. And what is also interesting is now it's used, I mean, not only similarly to what I say for B2S gamma, that you went from observing the decay, measure precisely branching ratio, then next is to study the properties of the decay, a property here in terms of lifetime, and the first result here is shown for constraining models which have an impact on the lifetime of the B-sub synthesis decay. Okay, and one more time, the last step is to use those information as constraint of a different new physics model, especially, of course, I mean, in the case where the measurement is close to the standard model, then you at least, if you're not completely killing the new physics model, at least you reduce significantly their parameter space. And yeah, here is probably something also, I didn't check all the lectures, but you probably had already or will have soon some illustration or about the model independent approach of collecting all these different important observable B2S gamma that I was talking about, which constrains the different component here in your this effective field theory, in your effective Hamiltonian, describing the different contribution here for obviously the operator photopenguin in the case of B2S gamma, but I just mentioned about B2S mu, and now I will go to B2S LL, and this is the observables we will be talking about. So B2S, you see, we were talking about B2S gamma with a single gamma that you observe in the final state, and now B2S LL, and the main two diagram in the case of the standard model, and let's say search window through those possibility of contribution from new physics. Again, so in terms of decay rate, I mean, you have two order of magnitude smaller than the E2S gamma, and rich potential in new physics in the sense of the branching ratio, but not only, as we will see, so many observables here can be formed. You have a three body, and so you can include also some other asymmetry and some angular distribution. I will not go through angular distribution because probably, or very quickly, but probably Guy will describe those kind of analysis. There is also two ways to go at it. I mean, one is let's say the first steps, which is exclusive decay. So K star LL is the same, or KLL in this case also. And inclusive. In terms of inclusive, there is a lot of some activities, quite a bit of activity, and this would be, let's say, in the future developed in Belle II, but no result to my knowledge on the inclusive part. It's much more difficult, in fact, because in the previous case I explained, then B2S gamma, you had very few gamma coming directly from a B, except the one coming from B2S gamma. They had to go through pi 0 and eta that you could calibrate and subtract. And the rest of the gamma were coming from the continuum that you can use alpha resonance data to subtract to your candidates. However, in the case of B2SLL, there is plenty of lepton, direct lepton coming from B, so there is no easy way to estimate and control this background. Of course, there is possibility of displaced vertex, but this is yet to be shown to be sufficient. So let's go first on the estimation of the branching ratio for B2SLL. So we start here from B2S gamma, and actually I go from the diagram of B2S gamma to B2SLL, and the price to pay, sorry for that, is this additional factor, the decay of gamma into lepton. And so this time getting a bit, even after adding the contribution from the interfering box diagram, B2SLL is confirmed to be quite rare, very rare. So we are talking about 10 to the minus 6. Okay, and ideal place to look for new physics. So here there is a little subtlety, I mean, compared to previous decay. So here we will have in final state, let's say B to KLL, so 1 kaon and 2 lepton. But this is also the same final state that B to J psi K. This is here, this contribution, where the J psi decay into lepton. So now you have the same final state. So this is, control sample in some sense. This is well-known decay, but is a very dangerous background with the same final state. The advantage, obviously, is that the 2 lepton are coming from the J psi, and if you look at the Q square distribution, which is just the lepton mass square, and you expect that this contribution will peak in J psi. So the plot you will show of the observable of interest will be shown in function of this Q square. And very often this region around the J psi and the next harmonium side 2s will be hidden. And the rest of the distribution is in fact the contribution you extracted of B2SLL. It was first observed, this is why when I was we were discussing with Jim, I was mentioning that, yeah, like B to D gamma was first observed by Cleo. Then the first observation for 2 order of magnitude, you need obviously 2 order of magnitude more statistics. So Bell had the statistic to observe it quite early stage in 2000, the first decade. So you can see, you can play the game of identifying the 2 minutes and the KL and forming the B to KLL. So people, I was talking about different observables, so the branching ratio in function of Q square. Another quantity which is predicted by the standard model to be unity is in fact the ratio of branching ratio, B to K mu mu versus B to K EE. So different generation of lepton, and you can verify the universality, the lepton flavor universality. So in case of the pre-LHCb, so the statistics was quite limited. Here I illustrate for a low Q square. So the Q square beam, which is just below the JEPSI, one of the Q square beam below the JEPSI window. So here, for example, you have Q square axis here, and you have the 2 window hiding the JEPSI and psi prime contribution, which are very high, and the different observables. So basically, asymmetry that I was talking about earlier. However, as you can see, the systematic, statistic was quite low. And even measuring this ratio of, K mu mu versus K EE was given by the B factory in a single beam, not even in 2 square beam, with, you see, an uncertainty which was in order of 20%. So not a very precise measurement. So what we can say modestly is that the B factory measure for the first time the K star LL and observe for the first time K star LL, KLL, and made the first few measurements, but as I said, with not with a modest, with no granularity in Q square, and with still quite large uncertainty. Okay, in the case of LHCb, sorry, and because of the strengths of their muon identification, as we already talked, that's a mode, as we have seen for B sub S to mu mu, they can reach quite easily, especially at 10 to the minus 6, as I mentioned. So we have seen that they observe B sub S to mu mu at 10 to the minus 9. So just adding the K on, it's expected to have a large sample. So being able to measure things in Q square B, in several Q square B. And in top of it, which was not completely trivial for them, is they also quite efficient in terms of electron. And so they were, so it's possible for them also to do the ratio I was mentioning, RK star RK, the ratio of branching ratio. What they do though, they don't know the number of B they're analyzing, so they don't measure absolute branching ratio. What they do smartly is to use a control sample, a model, a calibration mode, if you want, which is usually very well measured by B factories most of the time. So a B decaying with the same final state. And this is exactly what I say for the JEPSI K, for the JEPSI K star. It has exactly the same final state than the BK star mu mu or BK star EE that I was talking about. So what you do is a double ratio, in fact. So you have the known branching ratio used, and you use exactly the same final state decay. And this double averaging ratio allows you, in fact, to access RK star without any problem. As I was saying, if needed to be illustrated, you can see here for a low Q square and the central Q square, the very clean signal. So you see the invariant mass for K star mu and for K star mu here. And the control sample, even in log scale, is so clean that you have only few contributing peaking background. But yeah, I just remind you, this plot is shown in log scale. And so this is both plot, as I said, for LHC B. And as I was saying, for EE, the situation is a bit worse. Of course, the resolution is much worse, and the efficiency is also worse, but it's sufficient. And this is very well illustrated with the Jepsi K star, where you see a clear and sufficiently clean, despite of losing definitely some resolution. Then you see a very clean signal for Jepsi K star. In the case of for the RK star, so you need the K star EE, and you see here the distribution you obtain. So you have to be, because of the worse resolution, you have to be extremely careful about the background estimation, and that's what is done in the different K star value. So why I show those results is because they are, as you probably know already, they are some of the hot topic of the in the field, where people have observed or at least see some evidence of deviation from the predicted value. So I was talking about different Q square value. Here you can see this RK star in function of 2 Q square beam. And you can see the prediction of different model of the standard model. You have a small effect here due to phase space, but roughly the expectation is at 1, while you definitely see some trend, some deviation. And the things which is important is it happens for RK star, so K star mu, K star versus K star EE, but also for K mu versus K EE. So here I summarize the result in one slide. You can see K mu here very cleanly, and also K EE at the right with the deterioration I was talking about in terms of resolution. But after careful study of the background, you are able to estimate the yield and get this ratio or this double ratio when you normalize to Jepsi K in function of the 2 Q square. And in the low Q square, this is for LHCb, this black point you see here, things are deviating also. So you have a central value, almost 2 sigma, a little bit more than 2 sigma away from the prediction of 1. So by itself, it's not sufficient to claim for observing a strong deviation, but accumulated with what we have seen for K star LL, it starts to be quite interesting. Here, I just, for the purpose of comparison, we push as much as we could with the Belle data sample. And you see, so in light blue here is a LHC latest or most, among the most recent result of LHCb for RK and for RK star in blue here. And you see this 2.5, so deviation in both cases. While for in blue, you have the result of Belle, the most recent, but you see that uncertainty are much larger, and you will need much more statistics. So this brings me to the projection. And so this is a result from Belle. And the advantage of Belle, the disadvantage is obviously that you have much less statistics at this stage. But the advantage is that actually the resolution of KEE is much better than in the case of LHC. So it's going to be very important and very crucial cross-check to compare to, to confirm or not that there is a deviation. So for that, you need statistics. So those results obtained recently by Belle allow you, in fact, to put the first point of a bit less than 1 inverse attobarn and how much statistics you need to observe the deviation. So we will need something like 10, 20 inverse attobarn to really claim an observation, assuming that the current central value of LHC is the true value. Okay, so this is an exciting sector and get a lot of attention because, as I said, it's among the most the strongest deviation we have seen or remaining until now. And a lot of activity in theory propose some explanation for those deviations. And among them, one which seems to survive the current constraint are the leptoquark. And this leptoquark model very often predict enhancement. So I would say that my naive interpretation is that actually we will see other deviation, but basically it's expected. So you see the ratio RK is that the muon, let's say, deviating, and I don't know, yeah, maybe I show it here in this plot. It seems that actually compared to the standard model, you have in fact a deficit of muon compared to electron. Electron seems more consistent with the standard model, then the effect seems to be more in the muon side. And for the other information which happens also in the third generation, we will see that those models explaining the current deviation also expect a strong effect at the third generation. So here I want some word of caution, to be cautious in some sense. It's like at this stage again, there is no claim for lepton flavor universality violation. There is some interesting hints. There is some evidence. There is some evidence in several cases. So that makes things very interesting. However, again, I think this word of caution mentioned by Sheldon Stone is that, in fact, statistics are obviously still marginal, and we need, as I said, of course, updated result of LHCb with more statistics, and the coming run will certainly help. And as I said, well, Belle II is coming right in time. I will offer a different environment and with this interesting sensitivity. So that's what happened. So this is the situation for the B2S anomalies. Now I want to go quickly on B2G tau nu, B star tau nu. So this situation here, I was saying that there is, this is a dominant decay, so semi-leptonic. So the third generation, we discussed very quickly in the first lecture, the semi-leptonic B2D nu nu, B2D nu as a dominant diagram. In the case of the B2D tau nu, the tau, is not as easy to reconstruct as the muon electron. The tau, so I mentioned it here. So in this illustration, you have the same case, epsilon 4s in the 2B, what I showed for B to S gamma illustration. But this time, this is in blue, the signal side. And as you can see, so you have the D star and you have the, of course, the B2 tau nu, so the neutrino from the tau neutrino, and the decay of the tau. Often, most of the time, or at least in a significant amount of cases, you are looking for the tau in leptonic decays. And it means that you have 2 additional neutrinos. So in the final state, you have a lot of missing energy, all these neutrinos that you cannot detect in your detector. So you cannot do this exclusive reconstruction that I was mentioning for K star gamma or for K star mu or K star PP. For that, you need, to improve the information you have on the final state and constrain the kinematic. And you can do that. First, you can reduce the background by reconstructing the other P, fully reconstructing the other P. That's what we call a beta gain. So reconstructing in one of the decay we have used at the beginning, the dominant one, then this is what we will call hadronic type. So you use all the possible decay, B2 pi, D rho, and so on, of reasonably well measured decay to reconstruct the beta gain. And as in the center of mass, they are back to back. So in fact, indirectly, you measure the direction of the D signal. So this is a technique of we are using of beta gain. We are using when there is a neutrino in the final state. So this is a very nice illustration. We use also another technique which called the semi-leptonic time. Instead of fully reconstructed, we allow the clean D star M nu reconstruction. So you have 1 additional neutrino, but the fact that having so many leptons in the final state helps you to reduce a lot the background. So this is also a nice way to reduce background and to enhance your sample in BB bar. So this is just as an illustration of one of the first measurements, among the first measurement and latest measurement of BABA using all the statistics available. And here, why I show this measurement is that it was the first to claim a deviation from the standard model. So in this case, so very quickly, you see in green the signal above the dominant background of semi-leptonic. And so you have a clear signal, and your observables you will be using is not directly the branching ratio of D tau nu, but the normalized branching ratio, this time D tau nu by D mu nu or D E nu in the case of D factory. So we talk about RD and RD star. And those observables were seen deviating from the standard model. And this is going to be better seen in the 2-dimension. So this was the observable I was mentioning, the ratio of the D tau nu, D star tau nu versus the branching ratio of this D lepton neutrino, D star lepton neutrino, which allow you one more time, especially when you use a leptonic decay of the tau, to cancel a lot of the systematic. So if you had the tau at the same mass than the lepton, this ratio will be 1. This will be the lepton universality. The tau, however, large mass of 1.8 GeV or so. And then accounting for this limitation of phase space, then you obtain a RD star expected around 0.3, 0.25 for RD star. So this is a standard model, and this is a summary of the Babar observation. So you see quite a departure from the standard model of this RD star value from Babar. So Belle has also result with the same hadronic tag method in blue here, and see also some less pronounced, but also some departure from the standard model. And then step by step, we were accumulating more and more observable. It's become a very active sector where Babar, Belle, and LHC B provided, especially Belle and LHC B these last few years, not only with hadronic tag, but introducing semi-elliptic tag, even with this difficult final state of the star tau nu, and even more to the force from LHC B, measuring for the unexpectedly, even for them, I would say, this RD star in the hadronic environment. I just put the slide here for reference, but it will be certainly discussed and described by Guy Monday. But here I just show a summary of all the measurement made by the B factories and LHCb. So we start to have quite a bit of information, and when you compile the whole information, you see a very similar trend that what you get from RK star, let's say 3 sigma-ish deviation from the standard model. So, of course, let's say the future of those kind of measurement is to improve by including more statistics from Belle II and from LHC. But in the case of Belle II, also improving this tagging method I was talking about. Those tagging methods, have an efficiency of less than 1%. So you can see that room for improvement here will have a huge impact on our sensitivity. So those efforts continue. And of course, we can play the same game than B2S gamma. It's like beyond the ratio, branching ratio, you can do additional observables, which will help you, like the polarization of the D star, the tau, will help you to identify what kind of new physics you are seeing. So for the last a few slides, I put side by side B2S anomalies. So this RK star deviation from LHCb, and this time in the tau sector, I mean, with a lepton being a tau in the final state, this RD star RD deviation seen by Babar and other experiments. So this is in this context that you tune your model, in fact, to explain those deviation. So an example of lepto-quark model, for example, is illustrated here in some recent conference by a talk by Gino Isidori, interested of explaining those anomalies. And so while you explain the RK star and the D star tau nu, you can also predict what to expect from other mode. So theorists ask us, what about B2K tau tau? So you measure B2K mu mu, B2K EE, and as you see from the third generation, you expect larger deviation. Some prediction are down of a large K tau tau, B2K tau tau effect. So this is one of the illustration of the enhancement you can have of the branching ratio, which is predicted right now in the standard model You see for k mu mu, it's in order of 10 minus 6. For k tau tau, in order of 10 to the minus 7 here, illustrated, I mean, here by those values for the standard model prediction, while it can be, those values can be greatly enhanced by a new physics model at the level of 10 to the minus 4. So the challenge here, because this is a very difficult analysis, you have 2 tau in the final state. So as you can see, if you have a leptonic decay of each tau, it corresponds to 4 neutrino. So I'm going very fast, but this is really the program of physics for Belle II, because until proven, it seems to be only possible, or at least with some advantage in the B factories. And the only measurement available is coming from an analysis from Babar at the level of 10 to the minus 3. So we have seen that, you know, possible enhancement in order of 10 to the minus 4 is possible. So there is a, you know, some interest to measure branching ratio at this level if possible. And so I was talking about this leptoquarks. This leptoquark, on top of predicting enhancement for B2K tau tau, they're also 100 times larger than the standard model or more. Also predict something which belong to the third categories I had mentioned, this lepton flavor violation mode, where in the final state, you will have 2 leptons of different flavor, which is forbidden in the standard model. So those are very exciting perspective, because I mean, if you observe this mode with a tau in the final state and a muon, then this will be a clear observation of new physics. Those are predicted in the case of the given model of leptoquark at the level of 10 to the minus 6. And yeah, there is several similar prediction from standard model, from, sorry, new physics model. And so in the case of Belle II, this is also for Belle and Belle II, a very interesting challenge, a very difficult analysis again, because you have a tau in the final state. But at the same time, we have seen that we could observe this tau nu, d tau nu. So the current sensitivity of the B factory, so with the single result from Babar and soon coming result from Belle, and in order of 3, 4, 10 to the minus 5. And this final state is also reachable by LHC, which has shown a recent result around the same 3 to the minus 5. So this is, you know, the summary of what Babar is showing for this mode. And of course, there is no signal, but it has a particularity that you are able to indirectly reconstruct by recoil mass, the invariant mass of the tau, and that's where you would expect this beam, you would expect some signal. And because you don't see no signal right now, you put a limit in order of few 10 to the minus 5. But of course, I mean, this is only with a limited statistic of half inverse at the barn, and you can do much more while the statistic increase. They became very recently, I mean, because of these anomalies, and say in B2S LL and G star tau nu, G tau nu, they became really exciting more than here you have a very nice a plot showing, in fact, for B2K mu tau that I was talking just now, and versus lepton flavor violation mode of the tau, tau to mu 5. And you see the result obtained by Belle or LHC bar, and the allowed space from this new physics model, and the constraint you can have from direct measurement at CMS and Atlas. And you can see that, even with the 3 versatile bar, I mean, you still have quite a sizable room. And this indirect search measurement of the lepton quark, I mean, you are now in order of 10 to the minus 5. And so with more statistics, you will reduce or you will discover significant signal, and consequently could be interpreted as seeing the lepton quark. Okay, so maybe just a final couple of slides. I was talking mostly about B physics. I was talking at the end about lepton flavor violation in B decays. So B to K tau L, and where L is a muon or electron. But we also have to keep in mind that Belle II is also a tau factory. So in the cross section, this was the slide I have shown the first lecture. The cross section of BB bar is 1 nanobar, but the cross section of tau tau is also on the same order. So it means that we produce as many tau tau pair than we produce BB bar pair. So we are in this sense a tau factory. And in a very similar manner, and that's why I have shown this constraint combining tau lepton flavor duration and B lepton flavor violation, you have some interesting mode to search for. Some mode which are heavily suppressed because only possible through neutrino oscillation from the standard model. And so, I mean, at our sensitivity, basically 10 to the minus 40 means basically forbidden decay. So you really belong to the last category I had mentioned, where you don't expect in the framework of standard model to see any a signal 10 to the minus 40, it should be a minus here. And the final state you look for are basically the phi mu I mentioned earlier, or here's a tau in 3 muons or tau to mu gamma. And here, this is really, the B factories has a rule completely in this field, and has unfortunately not seen any signal until now, but has probed many possible final state, and you see here all the effort made from the mu gamma 3 muons I was talking about, but also many other combination. And from the Cleo time to, I kind of down a loop, in fact, from the first plot I have shown in the BCBS mu, where you have seen all this generation of experiment trying to improve the limit. And here you have 3 of them, where you see Cleo result on few 10 minus 5, then the B factories and Belle getting the most constraining limit at few 10 to the minus 7, and Belle II with 2 order of magnitude will be able to probe at 10 to the minus 9, 10 to the minus 10, where it's getting interesting in some sense, because you see that different possible new physics model will be probed and are predicted to show up at this level. Okay, so I mean, yeah, in the last slide I was just mentioning that this even 3 million case is a bit I mean, it's very challenging at the LHCb environment, but so it means that we will have to work hard in Belle II that the community is expecting us to deliver result in the tau sector also. Okay, that's all. I'm just thinking almost perfectly in time.
Okay. Thanks, Karim.